Hello everyone. Today we're going to start on 8.2. So 8.2 we are trying to talk about some application on using line integral. So before we do that, actually we're going to review a concept that you have learned in BC calculus, which is called the arc length. So if you remember, you actually learned about arc length back in BC calculus, where you actually learned two different formulas, if I remember correctly. So let's start with the first one. So from BC calculus, so let's say given two formulas. So I'm going to start with the first one. Let's say given a curve y equal to f of x over the interval from a to b, the arc length. So the term arc length is basically just mean length, is how long a curve is. The word arc added in front indicate that it's not a straight line. So therefore, you basically try to follow along a curve. That's the reason why I call arc length. So the arc length of this curve is given by this integral, which I don't know what your last year teacher used, but in here when we use arc length, we actually use the letter S to represent it. S is equal to integral from a to b square root 1 plus f prime of x square dx. Okay, so here S basically represent the arc length. I don't know why we use the letter S for arc length, but that's what mathematicians usually use. Now, however, there's a second formula for arc length, which is what happens if the length is given as a parametric curve. So let's say given a parametric curve, basically x of t, y of t, over the interval from a to b. So important to understand is that the first case, a from a to b is x, go from a to b, while here from a to b will be for t, go from a to b. You know what, actually, you know what, I'm going to fix it right now just so that it's clear. Okay, then the arc length of this curve is given by the formula S equal to integral from a to b square root x prime of t square plus y prime of t square dt. Okay, so now if you think about it, this expression right here, this part right here, you probably remember learning it. That is technically speaking the length of the velocity vector, which is x prime of t comma y prime of t. And that is often referred to as the speed of the object. And therefore lead into this definition, where we can now define what we call arc length function that can now determine how long the curve is based on a particular time, and we call that the arc length function. And so here's the definition. Let's say given a curve alpha, I'm going to call alpha, with parameterization g of t over the interval from, let's say, a to b. Actually, you know what, I'm going to call it t sub 0 and t sub 1. Okay, so t sub 0 basically the beginning time, and then t sub 1 is the end time. That's basically what it is. And t is just the variable in between those two. we can define what we call the arc length function for this curve. As follow. We're going to define the function s of t, which is equal to integral from t sub 0 to t, the length of the velocity vector, which is g prime. The actually, I'm going to have to change this variable to a different variable because I don't want to have it confused with t. I'm going to go u. So s of t will be given by t of 0 to t g prime of u du. Note s of t sub 1 would equal to the integral from t sub 0 to t sub 1 length of g prime of u du, which basically represent the length of the entire curve. Because t sub 0 is the beginning point. If you put s of t sub 1, then you're basically finding the length from t sub 0 to t sub 1. Since the curve ends at t sub 1, that gives you the entire length of the curve. So this is what we refer to as an arc length function. To kind of illustrate what does it do, imagine that I have a curve. So here's my curve. So here at t equal to t sub 0, our position is, let's call it x sub 0. And then here at t equal to t sub 1, then we have a, you know what, actually, I'm going to go and call the beginning point A. And then here's my end point B. So what does the arc length function do is the following. Let's say somewhere down the line, let's say here. Here is where at t equal to some specific value. Okay. Then this would be the length that's traveled from there to here. So I'm going to just call that like some generic t value. Then this red line would basically be what is this is going to be. Nope, I'm going to have to use a different letter. Remember, I can't use t because t is on the upper limit already. So that's basically what this function does. So when I move t to a different value, if I make t a bigger value, then this point would actually move further down the curve, and therefore the integral will give you a longer arc length. And if I move this red dot all the way to the end where vector b is, then it will give me the length of the entire curve. Extremely important to understand that t is a time variable. It doesn't identify where we are. That's why I have to point vector A and vector B to identify the proper points. Now, what are we going to use this for? Well, one thing we can use is to use this concept to actually deal with things that form along a curve. But before I do that, I do also want to point out something important. In the arc length function formula definition, we have this expression . This part right here actually has a name. This is often referred to as the arc length differential. And the arc length differential sometimes is referred to as just ds, which is equal to the length of g prime of u du. So therefore, if you think about it, you could actually rewrite this expression into this one. Which now then kind of makes sense because you're basically integrating ds, and we know that the integral and the differential kind of balance each other out, and therefore just simply give you s at t. And of course, asset t would be a length from t sub 0 to t. Now, one application of this concept is to use it to deal with something called weighted curve. Or more accurately, imagine that the curve represents some kind of cable or wire. And we can now actually try to calculate the mass of this thing if we know some kind of density based on length. So if we let a given path or curve to represent, let's say, a wire or a cable, then we can find its mass if we know its density. And here is interesting is that the density will have to be some kind of mass per length. Okay, different than mass per volume, because in here we're assuming that, once again, these are assumptions that you want to write down, you can. The assumption here is that this path will represent a wire cable to have uniform cross-section area. So basically it would be just like a long bended cylinder where it has a uniform circular cross-section. So therefore, the only thing that influences the density, the mass, is based on how long this wire is, not by volume. Because in that volume calculation, the only thing that's changing is the length, while the base area or the cross-section area actually remain the same. So therefore, it can be absorbed into the density. So how do we actually calculate this mass? Well, let me show you. Okay, imagine that we have, let's say we're given, let's say we're given a curve alpha with a polarization g of t, where t go from A to B. And let's say we also given a density function, net mu of vector x, be its density function based on the position And of course, because this thing is a density function, we have to make sure that it is always greater than 0. And we already established that this is mass per length. So what happened is the following. So imagine that we have some kind of curve. And I like to draw a loop, so therefore I'm going to do that. Let's say here would be at t equal to A, and here would be at t equal to B. Important to understand is that they will identify this to be one particular point, and the position here would basically be given by g of A, and this one, the position will be given by g of B. So that would be the position. Okay, so that is a position. Now, imagine the following. Imagine somewhere down the line I have a particular point. Let's say here is at t equal to some specific value t sub k. Okay? Then its position would be g of t sub k. That would give us our position. What will be the density of the cable at this point? So we are assuming that this cable, even though have a uniform cross section, the density is actually can be different throughout the entire curve. So the density will actually be given by the function mu at the position that we calculate the density, which means in this case would be this. So now comes the big question. If the density is constantly changing, how am I going to calculate the mass of this curve? Well, first of all, number one, the mass of this curve, well, this path or this curve alpha will be dependent on how long it is. But at the same time, because the density is changing, I cannot simply just multiply the length of this curve by the density. So how do we actually proceed with this? Well, simple. This is what we do. We subdivide this curve by putting in different dots. So I'm going to just make some random dot. And I'll make t sub k one of them. Okay? And then at each of these dots, what I'm going to assume is the following. I'm going to assume the density between two consecutive dots is exactly the same. Okay? We're going to assume... maybe I would... you know what? I can do it right here. We're going to make an assumption. We're going to assume the density is fixed between two consecutive dots. Which is basically between, let's say t sub k and t sub k plus 1. So basically it will be this point and let's say this point. Let's assume the density is the same. If that's the case, I can actually now calculate the mass at this particular point. The mass at t sub k to t sub k plus 1, which I'm going to refer to as m sub k, will basically equal to, since if I assume the density is fixed, I can simply multiply the density by how long it is. And how long it is basically a difference in the arc length, which I'm going to call that the arc length differential. So therefore, that will be the density multiplied by arc length differential, which is ds. Or, if you want to think about it, is the density at t sub k multiplied by the length of g prime at t sub k dt. So that would give me the mass between t sub k and t sub k plus 1, which is basically like this part right here, which I'm going to kind of highlight. So they can be one of them. So now what I can potentially do is to just add up all of these different line segments between any two consecutive dots. If I do that, I will have an approximation of the total mass. So total mass, which I'm going to call M, will basically be approximately equal to the summation k from 1 to n m sub k, which is basically meaning is the summation k from 1 to n. And yes, I'm hoping some of you have a little deja vu, because you've seen this argument before, of the density at g of t sub k multiplied by the speed of the length of the velocity vector, which is the speed, at t sub k multiplied by dt. If you think about it, it makes sense, because that just simply gives you speed times time, which is length. Okay? And so that gives us a total mass, but an approximation. So what happens is, if I do want to have a good approximation, I can say that the total mass would equal to limits as n approaches infinity, k from 1 to n, m sub k, which is the density of g of t sub k, multiplied by length of g prime of t sub k dt. And that become our total mass, which you might recognize is the Riemann sum. And so now I can actually rewrite this Riemann sum and have it convert into an integral. So what would be my formula? M would equal to the integral from a to b, mu of g of t, length of g prime of t, dt. So that's the definition. So this formula gives the mass of a curve given by g of t over the interval from a to b with density function, mu of x. So that gives us the mass, provided that we have the length. So let's go and try an example. So here's an example. Let's say given a helix described by the function g of t equal to 2 cosine t, 2 sine t, t. And t go from 0 to 2 pi, I guess. Okay. And it could be equal to 2 pi or not equal to... Actually, I'm going to put it equal to 2 pi because it's not going to be the same point. Actually, it will be a point directly above it. So I think we're okay to have it equal to. Let's say we're going to define the density. Let the density at xyz be the square of the distance to the point 0, 0 pi. And what we're going to do is we're going to try to find the mass of this helix. So if you recall, this is basically how the helix look like. In this particular case, since we have a 2 involved the cosine and the sine, it will start at this point right here, which is 2, 0, 0. And then it will rotate and then to this point right here, which would be most likely be 2, 0, 2 pi, which is directly over the other points. And here's the point 0, 0 pi, which is kind of like right in the middle of this curve. And that would define the density based on how far each point is to this, each point of the helix to this one particular point. It shouldn't be too hard to realize that as it rotates to where t equal to pi, it will probably be closest to this point because it will be at level with it. And any point beyond that would be on the same circle but further up or further down, therefore will create a longer distance. So it definitely means that the density is not going to be constant. So how do we go about finding the mass of this helix? I guess I don't see why we can just go for it, so let's do it. So let's start with first, we're going to define the function mu of xyz. So the problem said that is equal to the square of the distance to the point 0, 0 pi. So therefore, I'm going to do that. So this will be a square of the distance. To calculate distance, I'm going to use distance formula. x minus 0 square plus y minus 0 square. Oops, I need more room. Plus z minus pi square. And I need the square of the distance, so therefore I'm going to put the whole thing in a parenthesis and square. And of course, you recognize that the square just simply cancels out the radical, which is the whole purpose of it, because I don't want to deal with a radical in this case. So therefore, this just equal to x squared plus y squared plus z minus pi square. So that's pretty good. So that's our density function. Next, what I need to do is do the density function at g of t. So therefore, I'm going to go and put density of g of t. And so if I do that, I just simply have to plug in 2 cosine t for x. So therefore, 4 cosine square t plus 4 sine square t plus z is t. So we're going to plus t minus pi square. And hopefully you recognize that these two things basically form the Pythagorean identity with a 4 coefficient. So therefore it just becomes 4. I'm going to draw a line. Plus this thing square, so I'm going to just multiply it out. That would be t squared minus 2 pi t plus pi square. So that's what the density at g of t is going to look like. I'm also going to find g prime. So g prime is actually pretty simple. There'll be negative 2 sine t. Oops. Negative 2 sine t. 2 cosine t. 1. And so the length of g prime of t would equal to square root of negative 2 sine t square. Oops. T. Plus 2 cosine t square plus 1 square. So notice that these two things come out to 4 sine square t plus 4 cosine square t. So that becomes 4 plus 1, which is 5. So that becomes radical 5. Is there a surprise that this has a constant speed? No, we already talked about this. When you have an object that moves at a constant speed, that's how it forms a circular motion or an orbit. So in here, this helix is definitely orbiting around the z-axis, and therefore it has a constant speed also. So now I think we're ready to kind of put everything together from the mass. So using the formula, the mass will be given by the integral from 0 to 2 pi mu of g of t, which is 4 plus t squared minus 2 pi t plus pi to the square, multiplied by length of the velocity vector, which is radical 5 dt. So therefore I'm going to pull out the radical 5. And I'm going to integrate this thing, so it becomes 4t plus 1/3 t to the third minus pi t squared plus pi squared t, evaluate from 0 to 2 pi. And so if I simply just type into my calculator and just get a decimal out of this, okay? So if I typed into my calculator correctly, this is what I got. 102.4199 something. So I would say 420. And that's 3 decimal places. Remember, we kind of follow the same rule as basic calculus and 3 decimal places. And that would be whatever the density unit is, which didn't give a density unit, nor we give we're given a length unit. So I'm just going to give it the answer with no unit attached to it. If the density is given to be like kilogram per centimeters or something, then we'll have a density unit. We'll have a mass unit. But I'll leave it at 102.420 for now. Alright, that would be it for today's video. We're going to continue some more on our next video. Alright, talk to you guys then. Okay, bye-bye.